Yes. Just 1 second. Sorry, actually, sorry. Okay, so welcome back to lecture 15 on Riemannian symmetric space. Okay, so last lecture we have defined an affine connection. Today we are really going to use going to give the motivation for the definition of affine connection. Before that, we use a word very frequently in mathematics, which is called something like canonical. So two spaces are very canonically isomorphic. There is a canonical map. So let us understand this word little bit very clearly. So let G is a group, and this you form this quotient space G by H. If you take X belongs to G, then if you want to define a map from G to G by H, then the natural thing which will come to your mind is X going to XH. Okay. So this map is sort of natural. For that reason, this map is called canonical. So P is a canonical map. Okay, so now consider this example. Suppose let B and W be two vector spaces. Okay, over same field F. Okay, over F, and suppose dimension of B is equal to dimension of W. Okay, so you know that these spaces are isomorphic. What you fix is just simply a basis B1, B2, Bn, and W1, W2, Wn, and you map B1 to W1, B2 to W2, Bn to Wn. So compare this map with the previous map. Here, this B1, B2, Bn is any DOM basis here, and W1, W2, Wn is any basis, arbitrary basis. And this choice is arbitrary. So this map is not canonical. So there is no canonical isomorphism between vector spaces W and B and W, because this choice is arbitrary, and so the vector spaces are non-canonical isomorphic. I hope you understand the meaning of this word canonical. So, and last lecture actually, so the thing is actually last lecture we have introduced the notion of Riemannian metric and Riemannian manifold. So actually, I always ask the question to BSc or MSc student. So what is the difference between norm-linear spaces and inner product spaces? So usually I get this canonical answer that a norm-linear space is an inner product space whenever it satisfies some parallelogram law of identity. Okay. So then I ask the question. So what is the difference between then what is the reason for introducing inner product space? You can study just normal spaces and you add one condition, this so-called parallelogram law of identity. So what is the reason that you are introducing inner product? So then I usually rarely get one answer. The reason is the right answer is that in the inner product space, you can define so-called the notion of angle. And for that reason, that whenever you are introduced inner product, first thing you are proved that so-called Cauchy-Schwarz inequality, and between two vector x and y, you can define this angle between x and y is cos inverse this x dot y by norm x and norm y. So to define this angle, it is necessary that this quantity should be lying in between -1 to 1. For that reason, this Cauchy-Schwarz inequality is done just after you introduce inner product, right? So the thing is, inner product is more relevant towards geometry. If you want to study angle, shape, and vagara vagara, so you have to really bring in somewhere inner product. For that reason, that when this and in case of Riemannian manifold, this is done by this so-called Riemannian matrix. Now, this is a very important thing, and today I want to discuss some important concept called affine connection. So, last lecture, actually, I have defined this what is an affine connection. Today, I am going to give an motivation for that thing, and in my opinion, this is the most important concept of Riemannian geometry. Okay, so let us see. So let M be a smooth manifold, and let P belongs to M and B belongs to TPM. Okay. So I am not assuming that M is a Riemannian manifold. Okay. I am assuming just it is a smooth manifold. Let Y belongs to D1M. Y be a vector field. So now our aim is to study how Y changes in the direction of V at P. Okay, so this question actually makes sense, and I don't. At this moment, we do not know whether this we can study this quantity or not. So let d by y. Okay, this is okay. So d by p is really this is uh, the rate of change of y in the direction of v at p. Okay. So we do not know whether this such type of quantity exists or not. But if that is, if we are able to define this quantity, then we will call this as covariant derivative of y in the direction of v at p. Okay. So what I will do, if I will draw my picture. So suppose M, and this is my P belongs to M, and since B is in the Chandra space, so I will get a curve gamma, so that gamma 0 is equal to P and gamma prime 0 is equal to B. So the thing is, okay. So if I want to define this dVyp, probably if you will think for a moment, and the most natural thing, if you will think for a moment, the most natural thing, most natural definition of dVyp will be limit t tends to 0. Okay, this is really y of gamma t minus y of gamma 0 gamma p by t. Okay, so this y is a really vector field here. Okay, so y this is say t say, so this is y of gamma t and this is yp. Okay, something like that. If you follow your usual method of calculus, then this will be your most natural definition. Okay. Now, first thing you observe that this numerator doesn't make sense, because y of gamma t, this belongs to a t gamma tm, and this y of gamma 0 belongs to t gamma 0m, and these are two different vector spaces. So this numerator doesn't make sense. Okay. So, and I also told you that in between two vector spaces there doesn't exist any canonical isomorphism. Okay. Suppose you are somehow, suppose there exists a isomorphism between T gamma Tm and T gamma 0m, canonical isomorphism, some P T0 between T gamma Tm m to t gamma 0 m. So and so that means if there is such an isomorphism, so p 0 t of this so-called y gamma t, this will belong to t gamma 0 m. Okay. If that is the thing, then we can modify our definition. This definition, modify our this definition. We can define like dvyp is equal to limit t tends to 0, p of 0 t, y of gamma t minus y of gamma 0 by t, and hope that this will be a well-defined quantity and will be independent of gamma, so that we can define this quantity by. So in order to define, so what did you learn? So we learned that in order to define this dvyp, so there must exist some kind of isomorphism between tangent spaces. Okay. And in other words, there must be some rule that should connect this so-called tangent spaces. And by that rule, you will be able to transfer, okay, or transport one vector from one vector space to another vector space. That rule is really will be related to something called affine connection. Okay, and the isomorphism which we will get, uh, isomorphism will be called parallel transport. Okay. Yeah. So this is okay. Now, so let us come back to our familiar manifold. This is Rn. We first see whether there is something called uh, parallel transport exist or affine connection. Can we define an affine connection? That's all. Then we will come back to our manifold setup. Okay. Now, so let P belongs to Rn and B belongs to say TPRn. Okay. So that means let Y belongs to D1Rn. And in the last lecture, I have told you that Y will be something like summation of I is equal to 1 to n, some yi del by del ui. Del ui with the coordinate vector fields. Okay. So, and this is my say point P. Okay. So since B belongs to TPRn, so there will be some curve gamma. So gamma 0 is equal to P and gamma prime 0 is equal to B. Okay. So suppose this is point my gamma t. So that means y of gamma t will be some light side. Y of this will be suppose this is the picture of y gamma t, and suppose this is the picture of my y p. Okay. So let us say yi gamma t. Okay. So let us say write y gamma t. So this will be usually I is equal to 1 to n yi gamma t del by del ui gamma t. And okay, so define this yp. So I is equal to 1 to n. So let us write here y gamma 0 here. Y gamma 0 del by del y of gamma 0. Okay. So I want to define a parallel map from P. Okay. We want to define some map pre T0 from T gamma Tm, okay, to T gamma 0 m. Oh, not m. This is Rn. Rn to T gamma 0 Rn. Okay. So now what I will do, I will define simply P 0t. Okay, let us use a place. So see, the thing is, what I will define, so I will define P0t y gamma t. So what I will do, I will just keep this thing constant, but I will just change this del by del ui gamma t by del ui gamma 0. So what will be defined P0t, sorry. So P T0 T Rn. So I will define this as P0t. This is something like yi gamma t, same thing. Okay. Okay, del by del ui of gamma 0. Earlier it was gamma t. I will just simply write gamma 0. In other words, actually, if you follow picture geometrically, this will be just I am translating this thing vector parallelly. So this is P 0 t I. Okay. So this is the thing, and so the map is really P0t. This is AI del ui gamma. This is the precise map. So this is our natural suggestion that so to define parallel transform. Now if I only define this what dv y of p, okay, so our definition is limit t tends to 0 p t comma 0 y of gamma t, okay, minus y of gamma 0 by t. So if I will put those things here, then I will get I is equal to 1 to n. Okay, so limit t tends to 0 yi of gamma t, okay, minus yi of gamma 0 by t del by del ui of gamma 0. Okay. Now look at this quantity. This is really derivative of yi in the direction of gamma, and this is actually same thing as I is equal to 1 to n. This is really v of yi del b del I del y. Okay. Now observe that in this case, this doesn't depend upon the choice of the curve gamma. Okay. So dvy dvyp doesn't depend on gamma. Okay. Now I have in the case of Rn I am able to define this dvy. This is covariant derivative of y in the direction of b at b. Now I want to let x belongs to d1 Rn. I want to define dxy. Okay. So dxy, and this is the covariant derivative of y in the direction x. Direction x. Okay. So on most natural definition, it will be so dx definition of dxyp will be d of xp, y, and p. And we know that xp belongs to tpm, so this should be our definition dx. Okay. Now this is our most our suggestion. This is the definition. Okay. So if you will really, but you know that expression of dbyp. So instead of b, you have to just write xp, right? So that will be I is equal to 1 to n. Instead of b, I have to write xpyy. Xpyi del by del p. Now xpyi, if you remember the definition correctly, this is really xyi of p. So del by del ui. Now we can free this variable p from both left hand side. So 3xy will be, this is I is equal to 1 to n xyi del by del ui. Okay. So this is the covariant derivative y in the direction of x. So one can
this you are defining for manifold, right?
not manifold. I am still in Rn.
Still in
I am
Rn. Okay.
Yeah, I am motivating that what is the what is the mean what is the motivation for affine connection. I am motivating. Okay.
Okay.
So okay. So one can check that dx of y plus z is equal to dxy plus dxz. So this is really second property. Dx of fy is equal to xfy plus f of dxy. Third thing is d of fx plus y z f of dx z plus dyz. Okay. This is really fi of xyz belongs to comma y comma z belongs to vector field d1n, and this f belongs to c infinity. So you see that this d actually is an affine connection on Rn. But I have written m here. This is really Rn. So hence D is an affine connection on Rn. Okay. So this affine connection is nothing but just a simple notion of derivative. Okay, for manifold. Okay, and so what we got that that if you have a parallel transport, so we are getting an affine connection on Rn, and also D in this Euclidean case, we have two more properties which will be useful in later. You check that this will be dxy minus dyx is equal to Lie bracket of xy. This is B is really x g of y z. This is really g of delta xy z plus g into y delta x. Okay. So okay. So what we got in we saw that in Rn there is a
What is G? What is G?
Oh, G is the Riemannian metric on Rn. Thanks. Okay. This is the metric Riemannian metric on Rn. This is important. Okay. So we saw that a parallel transport in Rn we can define parallel transport naturally, and that gives rise to affine connection. And now you will see that in manifold setup, if you really have an affine connection, that means we have in means secretly we have the notion of derivative there. If you have an affine connection there, then you can able to get parallel transport, and from parallel transform you can also recover the affine connection there. So let us start then. So now let M be any manifold. So let M be a smooth manifold. Equipped with an affine connection nabla. Okay. So this is called nabla, by the way. Okay. So let I, okay, subset of R be an open interval. Interval, and let gamma from I to M be a smooth curve. So then we can define this gamma dot T really T tangent spurs of gamma dot Tm. I have discussed that. Then one can show that so that there exists a vector field, there exists X belongs to T1M, so that X of gamma T is equal to gamma dot T. So now let this Y T going to this thing from I to this is really T belongs to I. Be a smooth assignment. Be a map so that this YT belongs to really T gamma Tn. And second thing is for F belongs to C infinity to M. This map T going to really YTF is smooth. So what I'm saying that in this along the curve you choose a vector Y gamma T, so that Y gamma T really belongs to the tangent space T gamma Tm. Okay, and this choice, the assignment T going to Y gamma T, YT, T going to YT. This is really smooth, and this is given by the second condition. Okay, so that is what. Okay, so this originally Y defined on this curve. Okay, YT. So it can be shown that there exists. So it can be shown that there exists a vector field Y tilde belongs to D1M, so that Y tilde of gamma T is equal to YT. Okay. So ideally YT was defined on a curve, but you can extend globally. That's what it is saying. Okay. And to extend that, one has to really use something called partition of unity, and you can do that. This is not a thing. Okay. So now I am giving a definition. This YT uh, T belongs to I. Okay, is set. Okay, so not really. You should write is said to be parallel along curve gamma if this nabla of gamma dot T yt is equal to 0. Okay, so this doesn't have any meaning. Star doesn't, this thing actually doesn't have any meaning, because nabla is defined on nabla makes sense when this lower argument x and y are vector fields, but y dot t and yt doesn't, these are not vector fields. Okay, so we have to give a meaning. So meaning of this thing, meaning, so delta gamma dot t yt is equal to 0, amounts to check amounts to checking the that this delta, remember this x and y tilde gamma t is equal to 0. This has a meaning. This gamma x is really is an extension of this gamma dot t, and y tilde is an extension of this yt. Okay, this x and y tilde are defined globally. Okay, so it can be shown that the parallelism doesn't depend upon the choice of L. Doesn't depend on choice of x and y tilde.
What is x and y tilde? Can you repeat, Muna?
Actually, see, the thing is, x is really, y tilde is a vector field. Y tilde is it lives in this curve, right?
Mm-hmm.
Okay, so I am saying that, suppose this equation, you look at this equation, delta gamma dot t and yt is equal to 0. Okay, so this doesn't make sense, because the affine connection actually takes argument delta xy, where x and y are vector fields. Okay,
From tangent space, tangent space.
no, x and y are vector fields.
Yeah. No, that's
No, not tangent space element, just only vector.
Yeah.
Muna, I
Yeah.
think he what he wants to know is what is x and y. So x is the extension of this tangent vector field, and y is any other vector field on the curve. Right?
What is extension? What is extension?
I am saying that
x is the extension of this tangent vector field of this curve. So you have a tangent vector at each point of the curve, right? So x is nothing but the extension of that. X is a vector field. When you restrict to this curve, it's become the tangent vector on the curve.
Gamma dot t.
Yes, gamma dot t.
I am saying that then one can show that there existence. It requires some work.
Okay.
There will be some vector field, so that x of gamma t will be gamma dot t. It requires some work. Okay, it is not trivial at all. Okay, so this is an extension of this gamma dot t. Okay. And similarly, yt was defined on this curve. Okay, but I can get a global vector field, so that y tilde of gamma t is equal to yt. Okay, and so delta gamma dot t yt is 0. This doesn't make sense, but this makes sense. Delta x y tilde gamma t is equal to 0. Okay, you understand? So if I can, and it can be shown that the parallelism doesn't depend on the choice of x and y tilde. Okay, and
what did you say? Parallelism
doesn't mean choice of x and y tilde. If I get another extension, for instance, y tilde have many extensions, right? Gamma dot t. Suppose x and x prime are x tilde. Manojda, is it clear?
Yes. Yeah.
It doesn't.
So parallel, you are saying that whenever this connection value of the connection is 0 along the curve, then you say that y tilde y is parallel along this curve, right?
Along curve gamma. Okay. Okay. So now let us to a so let P belongs to M and B belongs to TPM. Okay. Let gamma some I to M be a curve in N. Okay, so this is the thing. So we want to we want to study this equation. Delta of gamma dot T is equal to delta. Okay, sorry, Yt is equal to 0. And gamma dot T naught is equal to B. Okay, so we want to study this equation. Delta of gamma dot T, Yt is equal to 0 and gamma dot T naught is equal to B. And this is really okay. So this actually boils down to solving a differential equation, and by existence and uniqueness, there will be some solution, and that will be a global solution. Okay, so this is a trick.
No. What did you say?
So I want to study this equation. Let I fix a curve. Okay. Okay. So I want to show that I want to find a say vector field Yt. It is not a vector field, but it is a smooth association. You can see, which is parallel with respect to the curve gamma. Okay. And I have some condition gamma dot T naught is equal to B.
Yeah, so this solution only exists locally, right?
Locally, but there is a this is the thing, but it will exist locally, but in this situation means it will be globally, means throughout the whole curve I you can define the global situation. Okay, there are something, if you look back ODE, there are some criterion are there that situation where the solution will exist globally, and in this situation it will hold.
No, what is that condition? Because
Actually, I do
pi,
not remember, but I have checked it. Okay, means long back actually I checked. For instance,
by
for
existence and uniqueness, you will get local solution.
Local solution, and in this setup is just for parallel transport only. You will get a global solution. Okay, you check it. Okay, only this case is happen. For instance, if you look back the solution of integral curve or geodesic equation, then you will have solution only locally. But the concept for parallelism, this thing, then you will have a global solution. Okay. So by existence and uniqueness, there will exist YVT, which will satisfy star. Okay. So now I will define this so-called power transform. We define this is PT0 gamma from T naught. So I have taken T naught, right? Better than okay. So P1 and T naught. Okay, so here actually you T naught belongs to I, you assume. So T naught gamma from T gamma T1 M to really okay. So T of gamma So you really write it here T0 and T1 from T1 to T0. This P T1 T0 gamma. This is B. Okay. You take this gamma B. Okay. This is the initial condition B, and at the point T1. This is my definition. Okay. So first thing is really you will get that properties. So
What is V lower bar? What is this quantity?
this is y dot gamma dot T naught is equal to V. Oh, sorry. Yeah, thanks, Manoj. You are saving me actually. Okay. Sorry. Actually, this is y of T naught is equal to V, not. Okay, so I have to correct. Sorry. Let P naught. Y of T naught is equal to V. So initial condition I should put on Y. Okay, sorry. Thanks.
And this is V bar is V lower bar.
Little weird lower bar is nothing. So this is Y BT1.
Yes. Y so y of T naught is V, right?
Y of T naught is V.
And what do you mean by y V of T1?
There will be a solution.
Okay, there will be a curve starts with the not curve,
Y BT1 value of Y at T1.
y value of y at T1. Okay.
Pritam, are you getting confused or? Hello?
No, I am confused.
Okay, where you are getting confused?
What is that y again? I mean, yeah.
See, the thing is, okay. So let me explain this more clearly. It is better that you should tell actually this is a curve, okay? This is a curve, okay? So actually what, this is any arbitrary curve, okay? A smooth curve, and you have this gamma dot T there, okay? Now I want to really find a vector Y which is will be parallel to, so that values of Y of gamma T Y will be parallel with respect to this curve. Okay. If that is parallel, so what I can see, I will, in the Euclidean case, I will fix a point Y at T naught. Okay. So something like T of gamma T naught M. I will just fix this point T naught. Okay. I will fix this Y T naught. Okay. This is my initial condition. Okay. I want to get a vector Y so that Y will be parallel to this thing, this curve, along curve gamma. Is the question is clear?
Yes.
See, the thing is, this is a curve. I want to really get a smooth association. Why? So that this association is parallel this thing. Okay. Now, for that reason, actually, I have to solve this equation. So whether Y will satisfy this condition or not. Okay. Now, if you put some initial condition, so suppose Y of T naught, this is my T naught, is equal to some V naught. Then by uniqueness, existence of solution, then I will get a parallel vector field YT. Okay. Okay. This is the solution YV.
Just let me interrupt a little bit here. So, for example, you can take like constant vector field in Rn. Like you keep the coefficients as constant. So let's say a1 del del u1 then plus dot dot plus an del del un, where a1 up to n are constant. So those will be parallel along any curve. That vector field.
Pushtita, do you agree that?
Am I correct, Muna?
Yes, yes. Pushtita, hello.
Yes, yes.
Are
yeah,
you
yeah.
able to this?
Yeah, now it's
This
fine. Mhm.
this is the thing.
Yes.
Now what I'm saying that, so okay, so what is PT not T1B? Okay, so you solve this equation delta of gamma t, gamma dot t, yt is equal to 0 and y of t naught is equal to b. Okay, you solve this equation. Okay, then you will get some solution ybt. Okay, now so I have to define from, so you solve this equation ybt, and by definition this ybt1, this will be, sorry, this ybt1, this will be t of tangent space of gamma t1 m. Okay, now I am defining this map ybt1 as t pt naught parallel transform from t naught to t1 along the curve gamma.
Y by T1. I mean, YB is an tangent space.
yb
But
yb is defined on this curve, whole curve.
Mhm.
Then and so that yt is belongs to t gamma t m. Then ybt1 will be t gamma t1 m. Maybe is the SKR is here or not, or RPS?
Okay.
Maybe they can help you understand you better. So this definition is clear. Tapendu? Hello? Clear, Munal, go ahead. So this is actually, I could have taken some time, but this is T naught, T1 T naught gamma is an isomorphism. Sorry, properties. Okay. P T1 T naught gamma is an vector space isomorphism.
Muna, I have a question. So why do you do parallel transport only along the curve?
Okay, I really explained. That is the dvy. I explained that so they defined this dvy. Actually, I took a curve and take that thing.
Yes, that's okay. Let's now take any 2 points on the manifolds, right? So you have a tangent space at both the points. So can you define an isomorphism between those tangent space? Like parallel transport is basically an isomorphism of the vector space, right? But I think what you mentioned in I think previous lecture, that any 2 points you can join by a smooth curve, right?
But
By
this
connectedness,
parallel
etc.
transport is really will depend upon curve. Actually, do you know something called holonomy group, or do you know?
I am not really familiar with that.
Okay, so this actually by using this so-called parallel transport, they define something called holonomy group, and that is a very important thing actually. Like fundamental group, they study that thing, and it has a very deep. I don't know those. Let us not go into those things.
Okay, fine.
So so you take T naught T1 gamma. This is nothing difficult. So you just after the class just this is composition of parallel transform from T naught to T1 and T1 to Tn along gamma. This is actually P of T2 T naught gamma. Third thing is this is an isomorphism. So if you really take this P of T naught T1 gamma inverse, okay, this is really P of gamma T naught T1. Okay, so these are my properties of parallel transport. And this P T1 T2 gamma is called parallel transport along curve gamma. From T0 to from where? From T2 to T1. So means gamma T2 to gamma T1 actually. Okay, so we have this given an affine connection. We are able to get some parallel transport, and so from parallel transport, actually we can get the affine connection also. So this thing actually the theorem. So let M be a manifold, smooth manifold. Equipped with affine connection, nabla. Okay, so let x comma y belongs to d1m and xp not equal to 0 for some p belongs to m. Since xp not equal to 0, then they let gamma minus epsilon to m be the integral curve of x. Then delta xy at p is equal to limit t tends to 0 p at t 0 gamma y of gamma t minus y of p by t. Okay. So for proof see Helgason. Actually, whatever proof I will not do any proof today, so you can see everything in Helgason. See Helgason. Okay. So these propositions say that you can really get back the affine connection from the parallel transport. Okay. So this is the thing, and this is the way actually we have started with the this we have started defining this thing in case of Rn actually. This was the motivation for us in case of Rn. Okay. So this is the thing. Now let M, okay. So let M be a manifold. Okay, so in principle there exists infinitely many connections on M. Okay, one can show that many affine connections on M. But the thing is, if you take this Riemannian manifold, then there will be a one connection which will be useful for us. That is called Leibniz-Beta connection. Okay, so let M G be a Riemannian manifold. equipped then affine connection say blah blah letter gamma from I to N be a smooth curve. Nabla G is said to be invariant under parallel transport along gamma. And this parallel transport is really associated to this nabla, okay? Associated to nabla along gamma if so something happens G of gamma T2 parallel transport from T1 to T2 gamma U parallel transport T1 to T2 gamma B. This same thing as very this is G of gamma T1 U B where U comma B belongs to T gamma T1N and T1 and T2 this belongs to domain of domain of gamma. Okay. So let R gamma be smooth curve G is said to be invariant under parallel transport associated to gamma along to del nabla along gamma if this is happens. Okay. So now G is said to be invariant under parallel transport. If G is invariant under parallel transport along any curve gamma. So that was really for this was definition of invariant under parallel transport along gamma, but it is really just invariant under parallel transport. If G is invariant under parallel transport along any curve gamma, then G is said to be invariant under parallel transport. Okay, so and we have really affine connection is a very notion of derivative in the notion of derivative, and we call that as covariant derivative. Okay. So it turns out that one can extend this notion of covariant differentiation to whole tensor algebra. And for instance, if so, one can extend the notion of covariant differentiation to whole tensor algebra. Okay. So we do not need this, but we need some things. For instance, you can take if x belongs to set d1n and f belongs to c infinitive m, then this delta of x of f is really your xf. And if G is a 0 to tensor, 0 to tensor means it will take two vector field in the argument. You can take one can define this delta x of G yz. This will be really x of G yz. Okay. minus g of delta x y z minus g of y into delta x. One can get or define. This is not definition. Actually, you have to really make some rules for this covariant differentiation. Then one can show that delta x g y z is equal to this thing. Okay, so this is the derivative of this 0 to tensor. Okay, so now proposition. Let Mg be a Riemannian manifold equipped with connection nabla. Then following are equivalent. Last thing is G is invariant under parallel translation. Parallel transport. Second thing is G of, okay, so x of G of yz, so G of delta x y z plus G of y delta x z. This really x y z belongs to vector field T1. Third thing is really, and this is really what does it mean? This is means delta x of G is equal to 0. Covariant of derivative of G in the direction of G is equal to 0. See, the thing is, if you look at this G y z. Okay?
No, the last condition I didn't understand what you're saying.
Which condition?
In the sense of that above definition.
Okay, this delta x G is equal to 0. What does it mean?
No. That means how have you defined this? Okay.
Delta x G is equal to 0. Actually, this is not the definition. I am saying delta x G is not the definition. Actually, one can fix certain rules, or so. Actually, you have to extend the notion of covariant derivative to the whole tensor algebra. Okay. Then you fix certain rule like it will commute with contraction, delta xf is equal to xf or something like that. So then you can prove that. But because I am not explaining that, you can take also this definition. Okay.
I think the second condition is nothing but the compatibility with the metric, right?
That is what I am saying. G is invariant under parallel transport. So this first condition is the compatibility with matrix, right?
Okay.
Okay, so what I'm saying, you can think in this way. So G, Y, Z, okay? G depends upon the points. So G is a variable, Y is a variable, and Z is a variable. When you put X, there you are really differentiating this function G, Y, Z. This function of this element, whatever I am underlining now, these are actually, there are three variables, three elements actually. G F1, you can think like F1, F2, F3, F5. When you differentiate there, then there should be three terms. Okay, so first there should be some derivative falling on G, then the rest other things are fixed. Then you fix G and Z, then there should be some derivative will falling on Y and G, and no derivative on G and Z. Similarly, for the third thing. But if you look at this equation, second condition 2, then it says that there is no derivative on G actually. So now I want to define something called Levi-Civita connection, and this is actual theorem. Let Mg be a Riemannian manifold Then there exists a unique affine connection nabla. There's a nabla called Levi-Civita connection. Such that this thing what it would, so that first thing is x, g, y, z. This is g of delta x, y, z plus g of y nabla x, z. Second thing is delta xy minus. This is called torsion precondition. And meaning of first thing, you know that G is really compatible with matrix. G is torsion free or torsionless condition. Okay, so this is really the proof. Actually, you can see Helgason. As I said that I will not prove anything. So just okay. Whenever this is really in a Riemannian manifold, so and we are nothing is nothing is mentioned about conduction, then you will understand that that is nothing but your Levi-Civita connection. Okay, so that is basically your Levi-Civita connection unless mentioned. Okay. So let Mg be a Riemannian manifold with Levi-Civita connection blah blah. Then okay, so a curve gamma from I to M is said to be a geodesic if nabla gamma dot t is equal to 0 for t belongs to I. Okay. See, I have explained that this doesn't really make sense. Nabla gamma dot t doesn't make, because it makes sense to define del nabla xy. So like the previous case, you have to really extend this gamma dot t to a differential to a global vector field x gamma t, and you have to solve this delta xx gamma t is equal to 0. Okay, and one can show that this really this doesn't depend upon the choice of x. Okay? So this thing is really, so for instance in case of R3, if you look at our Rn, so this is nabla, so nabla gamma dot t is equal to 0. What does that mean? That means gamma dot t covariant derivative of gamma dot t is 0 in the direction of gamma dot t. Covariant Hello?
Munada, we cannot see your screen.
Okay.
Can you share it again?
I lost my connection actually. So I am doing it from Geo, but I think I am to enter. Actually, I am not able to share my screen. Should I join once more?
Screen, but
You can see our.
yeah, we can see your screen. You just share the notes.
You can see. Pritam.
Yeah,
So,
you can just see just
what-
the
what-
window.
Munad, the HRI connection is back now, I think.
Oh, that.
Yeah, I think it's back.
Okay. Do you see my screen now, Pritam?
Yeah, you
Hello?
can see the screen.
Okay. So where was I? Where did I leave? So a curve gamma from I to M is said to be a geodesic. If Pritam,
Yeah, now I can see the geodesic.
now where did I left?
Yeah, you can start after that. After the definition
After
of geodesic.
okay, delta gamma dot t is equal to 0. So if that will be called geodesic, but this definition doesn't make sense. So what I do, you just extend this gamma dot t to a vector field x, so that x gamma t is equal to gamma dot t, and you solve this equation. Delta x gamma t is equal to 0. And if you are able to solve this equation, you can show that this definition doesn't really depend upon the choice of x. Okay, so this is how it is. You have to make sense of this definition. And okay, so in case of Rn, you can see that covariant derivative of gamma dot t in the direction of gamma dot t is 0 really. So for instance, you can take a surface, you can interpret this gamma dot t as the velocity vector, and so since gamma dot t doesn't change in the direction of gamma dot t, so that means it has no really tangential acceleration. That means it has only so-called normal acceleration, or in language of physics, you can call this as centripetal acceleration. Okay, so that is not really important now, because we are really going to give some other characterization of geodesics. Okay, so now proposition. Uh, let okay, so okay, here is a definition. So, definition: a geodesic uh, is called maximal geodesic if it is not restriction of if it is not a proper restriction of any geodesy. restriction of any other geodesy. That means this geodesy cannot be extended. For instance, in case of Rn, if you take a straight line segment, then you can extend it. In case of say R2, so you can extend it. So this is not a maximal geodesy. Okay. So proposition, let Mg be a Riemannian manifold with Lebesgue beta connection nabla. So let P belongs to M and 0 not belongs to V TPM. Then there exists a unique maximal geodesic gamma PB, okay, with gamma 0 is equal to P and gamma prime 0 is equal to V. Okay. So these two conditions actually really it uniquely determines this. I should write it gamma P pro 0. P0 is equal to P and gamma PV prime 0 is equal to so-called okay. So yeah, proof you can, I am leaving it. Proof actually CL gas, and this is actually here one interesting thing that this you cannot really have a global solution here like the parallel transport case. Okay, so you can really get a geodesic in an interval or so domain of what I'm saying, that if you take domain of gamma P gamma V, so domain of gamma P gamma V, let us say AB say. So it may happen that A is equal to minus infinity, B is equal to infinity, A, B are finite, and one is infinite and another is finite. It may happen, all these cases will happen here. Okay, but the thing is because of these two conditions, this and uniqueness, so remark if two maximal geodesics agree at a given point and has same tangent vector, then they coincide. Really, then they coincide with each other. Okay, so this is the thing. Now there is a theorem or proposition. Let N be a Riemannian manifold. Okay, and in the Riemannian manifold, I have told you that with distance d, there is a distance function in there. Let P comma Q belongs to M and gamma be a curve in M joining P and Q, so that length of gamma P comma Q, the length of gamma P gamma is equal to dP comma Q. Then gamma is actually geodesic. Actually, you can, in place of curve, actually you can here take gamma be a piecewise smooth curve. I have defined the notion of curve for this smooth curve, length of a smooth curve, but you can naturally extend the definition of a length of gamma, where gamma is a piecewise smooth curve. You can give a definition of length of a gamma, and it says that if length of gamma is a curve joining P and Q, so that length of gamma is dP P comma Q, then gamma is a geodesic. Okay, so proof actually you see Helgason. And another thing is if really if gamma is a geodesic, then actually one can prove that this this has constant. Norm of gamma t is equal to constant, or t belongs to domain of gamma. So what does that mean? That means this is C of gamma t, gamma dot t, gamma dot t. This is constant. T belongs to domain. Okay, so now this is a important proposition. Now I want to really give a most important theorem. Okay. Okay, so actually, no, I have to define something called an exponential map. Okay, so let M be a Riemannian manifold. And P belongs to really M, and P belongs to TPM. So I take this thing, let gamma P be the unique maximal geodesic. Geodesic with gamma P0 is equal to P and gamma prime 0 is equal to P. Okay, so it may happen that one may or may not, one may belongs to domain of gamma P comma B, or it may happen that one may not belong to domain of gamma P comma B. Both the condition may happen, but what one can show that if this B, okay, if this norm of B is sufficiently small, okay, or B is sufficiently close to the origin 0, then one will belong to domain of gamma P comma B. Okay, so let me just let me explain a little bit. The TPM is really isomorphic to Rn, and this is the map AI del by del yp. This is really A1, A2, An. Okay, so I can really import, borrow the norm from this TPM from Rn. So if this norm of B, if now, so one can show that there exists an epsilon greater than 0, so that if this norm of norm of B is less than epsilon, then one belongs to domain of gamma p comma v. Okay. So then gamma p, I will define this exponential of p is really gamma pb1, and gamma pb1 belongs to this is n. Okay. So now this is our exponential map. So I want to give a theorem, then you will stop here. Theorem. So let M be a Riemannian manifold. Then there exists a neighborhood. Let P belongs to M. Let P belongs to M. Then there exists a neighborhood 0 and 0 of 0 in TPM, so that and 0 in TPM and the neighborhood and an open. Here is open neighborhood. Neighborhood UP of P in M, so that this exponential map P exponential P from N0 to UP defined by exponential of P is a diffeomorphism. Okay, so proof actually Helgason. So remark this and actually I have really there is just a open convex. You also this is not required, but you always take this open convex. Okay, remark the neighborhood N0 and NP are called normal neighborhood. So normal neighborhood are those where this exponential map is called normal neighborhood. Neighborhoods. So let us write a last theorem and we will stop there. So we have actually okay then last theorem and just stop here. Okay, last theorem. Okay, just theorem that MBA Riemannian manifold with distance d, then each p belongs to m corresponds to a number rp greater than 0, so that if 0 less than rho less than equal to rp, then first thing, this is the ball b rho p, and this is the set of all q belongs to m, so that a distance of pq less than equal to less than rho. This is normal neighborhood of each of its points. This is normal neighborhood of each of its points. this point. Second thing, if A comma B belongs to B row P, then there exists a unique geodesic gamma A comma B joining this A and B, joining moreover this gamma A comma B is the unique curve in M, so that length of gamma AB is really distance between A and B. So proof C. Helgason, and this theorem will tell that geodesics are locally distance minimizing. So last remark. Sorry. Remark the above theorem says that the geodesic are locally distance minimizing, or locally length minimizing. So just so as soon as so just look at this statement, and tomorrow you see that if there is some problem in the understanding this statement, you just let me in the next lecture. I think I should stop now. Is there any question? Pritam, I am leaving. Okay.
Okay, so I'm stop recording.
Okay.